everybody. We are Team 42, and we're going to be presenting on process improvements to the Vibrum batching of rubber compounds.
My name is Aaron.
I'm James.
I'm Stefan.
I'm Ethan.
I'm Stella.
So we're just going to start with a little bit of background on Vibrum as a company. Vibrum is a manufacturer of performance rubber soles. They produce about 40 million soles plus per year. And they are headquartered out of Aldersati, Italy, and they have manufacturing facilities in North Brookfield, Massachusetts, which we were able to visit, and Guangzhou, China. They are lead producers for the U.S. military boots and their contracts, first responder boots, and for outdoor enthusiasts.
So the first part of our project was to understand the overarching problem that Vibrum faces. So last semester, our team and I had the opportunity to visit the North Brookfield facility down in Massachusetts, about an hour drive away, where we observed the entire manufacturing process of these rubber soles. Our project revolves around the first part of this manufacturing process, which is the batching of the rubber additives. Currently, Vibrum employs a manual process to batching these materials, manually scooping material by hand. And although this process is what Vibrum has been using for quite a while, it does come with a lot of flaws that does lead to a substantial loss of profits. So the current process results in about a high rate of bad batches. So about $96,000 is lost every year. That's 2 total bad batches created every week, about 104 bad batches a year. About $1,000 every bad batch accidentally created is discarded. So from our observations, we noted that the bad batches are coming from 2 things. The first being the wrong material is being selected, whether extra material is added or required material is completely omitted, and the wrong amount of material is added, whether too much of a certain material is added or not enough. To set the scene, this is what the current Vibrum batch creation workspace looks like. There are about 20 to 30 material hoppers lined up along an aisle side by side with a mobile weighing scale that can be moved up and down the aisle by the worker. The worker looks at a printed recipe sheet that's printed the day of and goes from hopper to hopper, scooping material out of the bin and putting it into the weighing scale. This picture is what a completed batch looks like once the worker has completed scooping up each of the required materials for a given recipe. It is then packaged up in a plastic bag, put into one of those blue bins and stacked up, awaiting for further processing.
So based on Aaron's introduction, we just identify some key inefficiencies in their process. The very first of all is that because their entire process is done by a worker manually and the worker is only relying on a sheet of bill of materials, like they have to read it, but the sheet itself is very hard to read, both due to the dim lighting of the factory and the sheet itself is not well organized. Another thing is that during the entire bending process, there is no process they need to check to ensure the correct material has been selected for the recipe, and we have to improve that. Another thing is due to their measurement. If their scale is not accurate enough to measure certain recipe materials, especially when dealing with large quantities, the precision is just not enough. Another thing is that because they mix everything together and there's no way to check if the raw material is selected and there's no way to remove a certain material. So even if one material has been selected incorrectly, the entire batch is just a waste, which will cost thousands of money. So with that in mind, we have to improve their system. So we decided because we are improving to their system, we have to maintain some of the parameters of their current system. So we decided production rate is about 100 batches per day, and each batch will contain from 15 pounds to 50 pounds of different materials. Also, for the storage system of what they currently have is about 80 pounds for each material. And also for the accuracy of the scale is about plus or minus 1% of accuracy. And based on the production rate we have calculated for each batch, we have to we have to make each batch processing is about 3 to 5 minutes. Also, like there are 20 more ingredients, so our system have to compatible with at least 20 ingredients. So we decide to improve the efficiency and reduce the error of their system, and also like our system have to easily adapt it to their system and their current recipes, and we have to like have a budget limit because like there are some systems on the market you could buy directly about $100,000, but we have to take that in mind because we are improving their system, so we have to like deal with this limited budget. And also Vibrum insists that human must could involved in the entire process so that they could change the recipes.
So with those requirements in mind, we began to investigate what already exists out there. We started with what Vibrum investigated first. So you can see those on the screen on the left. Those are 3 systems. And as you can imagine, those are professional systems. They essentially work off the shelf for what Vibrum needs them to do. They have high degrees of accuracy and they also have high throughput. They're able to fulfill most of those requirements that we outlined before. However, the biggest issue is the cost there. They are far more than Vibrum is willing to spend at this time. And so we began to look into other solutions of machines that already exist in industry or that are used in industries like agriculture, pharmaceuticals, mining and mineral extraction, essentially anything that would have to deal with like a fine powder or some small chemical like that. And you can see some of those machines on the right. Generally though, our finding with those is that while they do fulfill some of the requirements, there's no magic bullet solution there that it will just work off the shelf or with minor modification. So with those findings in mind, we began to look for other solutions to the problem.
So yeah, as stated by Salem, there are solutions to this problem exists, but the limiting factor being cost. So our role with Vibrum was to see how much value could we generate with the least possible investment. And that kind of comes down to the 2 major errors, the material selection and then the measurement error. On the material selection side, we came up with this sheet revision, a light and lock system, as well as some other ergonomic improvements to the workspace. And then for the measurement side of issues, we specified some cheaper off-the-shelf solutions that we think could achieve Vibrum's goal. So starting with those measurement solutions, given our budget and what Vibrum was willing to invest with us, there was nothing that we could produce that could achieve what exists on the market already. That being said, there are some pretty cheap options that we think could help solve their measurement problem. The simplest being a more precise scale. The scale that Vibrum has just isn't precise enough for their small ads. They need 1% accuracy, and their scale only reads down to 0.01 of a pound, which just isn't enough. They could put this smaller scale next to their current scale without really changing much else, and that would give them the precision they need. But that doesn't eliminate the potential errors with the worker. A secondary solution would be to add one of these powder filling machines from Bever or a similar distributor. These systems are not automated on their own, but can be bought for a couple $100 and then could be integrated into a full PLC system later. Vibrum could just purchase a few of these machines for their small ads, or they could replace their entire line. Even though these machines cost more than what we were able to purchase, given our budget, it still puts the total cost significantly lower than the fully automated machines on the market. As for the material selection improvements, we designed a sheet overhaul. As stated by Aaron, the current sheet is really small and hard to read. It's more or less just a printed Excel sheet, which makes it easy for the worker to misread across the rows. So we just made an Excel worksheet that takes in Vibrum's current format and outputs a new sheet in which all of the material names and quantities are in large, bold font right next to each other. Each material as well has its own color key to it. That way you can't accidentally mistake one material for the next. On top of that, we created an augmentation to their hoppers. So we made this light and lock system, which gets added onto the front of each of the hoppers. How it works is if a material is in a given recipe, that light turns green. When the worker then goes to that bin and opens it, the light turns yellow. That way he's informed that that material has already been used. Any material not used in a recipe will not light up, and the magnetic latch will turn on. The purpose of the magnetic latch is to alert the attendant if he's opening a bin that's not in a recipe. Though we didn't want it to be a full lock because there are scenarios where there needs to be last second changes to a recipe. On top of that, this entire system is controlled by a laptop computer at the front of the line. It takes in data from an Excel sheet and then uses Python code to distribute that to all the boxes. So it's auto updated with every recipe.
So next, taking a look at the bill of materials, The main components used in our prototype that actually derived the most cost were, interestingly, the set of lights. We only used 3 small lights for each boxes, and these actually totaled upwards of $40 for the 3 lights themselves. In addition, we had to include different adapters that would ensure the watertightness of the box so that dust or some sort of moisture would not get into the box and ruin the electronics. Going back to the lights, actually, the reason the lights are so expensive is because they include a gasket in them, which would allow them to be inserted into the hole and then sealed so that it's watertight. Additionally, the microcontroller we used is an Arduino Nano, which is relatively expensive compared to what you would mass produce using a printed control board. So in total, our prototype cost $110 in just components for one of these small boxes that would be added onto the hoppers. And we estimate that through manufacturing in quantities of 100 by mass production, that would actually be reduced to $20 in components, $5 for labor and assembly, and $15 for the CNCing and the machining of the box and the system as a whole. Additionally, our system, as Ethan described, uses a laptop at the end of the system. So you need to buy the laptop, which would be roughly $300. And then it uses a system of USB hubs, which is daisy chained to the computer in order to provide the sufficient power for our system, in addition to allowing the data transfer to be going from the computer and to all the different boxes, such as maybe 20, 30 boxes.
So, and here is the result of our solution. So based on our research, about 30% of the error is due to material selection, and about 70% of the error is due to the measurement. But our budget is limited, like each scale on market will cost about thousands of dollars, which is way more than our budget. So we decided to do the most cost efficiency solution, which is eliminate the material selection error. So with our solution implemented, the material selection error could reduce more than 90%, which will result $26,000 saving for Vibrum per year. And the entire cost of our system is about $2,000 and for like all the 20 bins, but also like the cost is estimated based on our prototype. If we went on to mass production, the cost could went down even more.
So we actually had the opportunity to go back to Vibrum, show them what exactly we worked on and get their feedback on it. Overall, they liked the box. They liked that it was comparable to in function to solutions that they already looked into for that already exist out there on the market. They also, though, really liked the price point for it. It was significantly cheaper than other solutions that were considered before. Additionally, they liked the sheet and they saw how it could be useful, and they may implement that in the future. The biggest thing, though, that they were interested in is actually our findings with the measurements and scales. It seems that that's the primary method in which they want to move forward with. And just in general, the reason why they've actually been hesitant to adopt the light system is because they ideally want some kind of measurement system off the shelf that they can implement and eventually eliminate the actual worker on the line, because they see human error, regardless of how involved the human is or what mechanism by which you limit that human error, is still to be the problem in play. So if we were to continue to work on this problem, we would definitely look more into the measurements moving forward, and we would come up with some entirely automated solution. Now, just in general, though, the takeaways from this project, because we learned a lot throughout it, the biggest one is probably that engineering is a process, right? It's a set of critical thinking tools to solve a problem. It's not just going out and building some kind of gadget or gizmo to achieve a solution. It's thinking critically and being able to work through and find solutions to the problem. The second thing that we learned is that there's always going to be some ideal solution, right? Where if you just throw money at the problem, then the problem goes away. But you also have to work under the condition of scarcity. And so the actual solution that you end up implementing is somewhere in between that, between scarcity and like the ideal solution. And then just the final takeaway that we had is that sometimes the work that you do for the client is showing them why they need to adopt solutions that they've already looked into, and that there's truly not another way around the problem to at least achieve the end states that they want. At this time, are there any questions?
So, besides these bad badges that they quantified for you. Could any of the measurement improvements that you suggested, maybe even material selection, could it make any positive gains for them in terms of the quality of what they typically put out? In other words, the stuff that they deem acceptable that they sell, would it by any chance be better than it is now?
So how it works currently is every batch after it's been completed is tested by their chemist. And they have their own limits for what that is, which they didn't tell us. So
Okay.
we don't really know.
Sure.
Ideally, yes, but unless we have hard data, it's hard to.
Okay.
And just another thing on that is one issue that the chemist actually acknowledged is that they're always adding things to the recipe, but they're very hesitant to take away any chemicals. So if they were to spend the time on their end to actually look at the various balances and again, try to reconstitute the recipes, then that could potentially help with material selection. But again, that's something that's beyond the scope of this project.
Can you explain again how the this box with the light that goes on? You explained it, but I didn't understand how it works. And it seems like it would be open to some uncertainty. How accurate is it?
Yeah, so the reason we developed it is there have been cases where the worker either omits a material in a recipe or accidentally kind of double includes a material. And that problem isn't found until the entire batch of rubber is made, which leads to the wasted material. How this system works is they get their batching sheet, they have their recipes for the day. So this gets uploaded to that computer. And then each recipe, as the worker goes through the day, all the bins used in that recipe will light up green. So that way the worker knows only go to these bins, don't go to anything else. And then as he goes through each bin, that toggle changes to yellow.
So it's more about the workers.
Yeah,
The worker was making the mistake. And now with
This
the
is a
lights,
check.
the worker
yeah,
is not likely to make a mistake.
exactly.
So it's not measuring the
No.
recipe material.
It's only for selecting the right materials, not for measuring the quantity.
Got it.
Any other questions? We have time. If there are no questions, can you please give a round of applause?